Hey everyone, welcome to our next video. This one is 5.5. This is our last section in chapter 5. And this is applications of vectors. Whenever we talk about like applications of something, usually it's word problems. So that's what we're going to be working in today. So in this section, a big thing that we utilize with some of these problems is parallelograms. So I want to remind you some things about a parallelogram and some just geometry stuff in general. One, in a parallelogram, opposite angles are equivalent to each other. So those are the same, like the ones that are opposite. Opposite sides are also the same. Not only are they the same length, but they're also going to be parallel with each other. So something that we should know is, like going to some geometry stuff, is that two angles that lie on the same line are supplementary. So what we will see here is that adjacent angles are supplementary. This means that they add up to 180. So like these angles right here are supplementary angles. So if you add them together, they should add up to 180. So that's going to be something that we'll use sometimes. Also, just some geometry review. If you have two parallel lines that are cut by a transversal, we can see some different stuff. One, alternate interior angles are equivalent to each other. That's actually why, like, if you cut this parallelogram in half, you're going to see some alternate interior angles happen, which we will do sometimes, like cut it in half. And then also the other one that I want to point out to you is that corresponding angles are equivalent. So an angle here and an angle up here, they're in corresponding spots, like right above the parallel line. So those are going to be equivalent to each other as well. So those are just some different things that we'll see throughout this section that I thought would be good to just bring up in the beginning. So let's go ahead and work on our first example. It says that two horses are pulling on a tree stump with forces 200 pounds and 300 pounds. If the angle between the forces is 65 degrees, what is the magnitude of the resultant force. And then it also asks, what is the angle between the resultant and 300-pound force? So of course we should draw this out. So I'm going to start off, we got our tree stump. Let me just go ahead and draw that first. There we go. There's my little tree stump. Kind of looks like a little pie. And then it's saying that these horses are pulling on the tree stump, and the angle between their pulling, like the two horses basically, is 65 degrees. So I'm going to say that maybe one horse is pulling this way and maybe one horse is pulling this way. And this inside angle here is 65 degrees. So let's say that the green one up here, let's make this one 200, and then down here we'll make this one 300. That is going to make it a little bit longer. That's not really something you have to worry about, but just so you understand, like as I draw these, sometimes I'll make certain things, certain lines, like certain lengths, and it's usually based on the magnitude. So if something is like a bigger magnitude, a bigger force, usually we would draw that a bit longer. That'll be a little important for when we draw out, like later we're going to do some airplane problems, and you'll kind of see why that might be helpful to draw it well. So let's see, what we're looking for is the magnitude of the resultant force. So think about like where this stump is actually going to go when it gets like launched out of the ground. As both the horses are pulling, it's not going to go straight with the 200-pound. It's not going to go straight with the 300-pound force. It's going to go somewhere off to the middle, probably a little closer to the stronger force, but it's going to go something like this. So I'm going to call this R. This is my resultant force. And then I'm also looking for the angle between the resultant force and the 300-pound force. So I'm going to go ahead and label that theta. And so I can actually make a parallelogram with this information. So let me try to draw it better than that. I might have to extend the blue a little bit. Let's see. Okay. All right, that looks okay. And then for the green, yeah, there we go. And that does make me have to extend that a little bit. Just for my picture, I mean, I'm just trying to draw it nice for you, but it's not really that serious. So the reason that I did this is because now we can see that we have some triangles, and that's always going to be helpful. So I also know that because it's a parallelogram, this side is also 200. This side up here is also 300. And then I brought something else up earlier. I said that the angles that are next to each other are supplementary. So that means that, I'm going to pick another color, this angle and this angle should add up to 180 degrees. So I can get this angle over here that I'm missing. So 180 minus 65 gives me 115. So now at the bottom here, I'm seeing this new triangle like form. I'm going to draw a little sketch of it just to kind of blow it up a little bit. So this is 300, this is 115, this is 200, this is my R, and this is my theta. So now I have a triangle that has a side angle side relationship. So we can use law of cosines. So first I'm going to go find R since it's across from the angle that I know. So let me write out the law of cosines real quick. So that says, I'll just write it with one of the letters of like A, B, and C that we used before. So if I have like C squared, it's equal to A squared plus B squared minus 2AB times cosine of C. And so when we're looking for R, it's going to be R squared is equal to, and then just my other two sides are 300 and 200. So I'm just going to plug those in as A and B. So 300 squared plus 200 squared minus 300 times 200 times cosine. And then the angle between the two sides or across from R is 115. I'm going to go ahead and solve this and plug it into my calculator. Be careful, make sure you also take the square root of both sides so that you can get R and not just like R squared. I'm just plugging into my calculator. I don't like to always go off of my notes because I worry like what if I wrote something wrong and um, need to like fix it or something, you know. Cosine 115. Oh, I forgot my 2. Sorry about that. I forgot this 2 right there. That needs to be in the formula. I was typing it out and I was like, I'm missing something here. Something's wrong. There we go. And, okay. Take the square root. So I get 425.1 and then it's just 0 after. I usually like to do 2 decimal places. And so this is my resultant force. And so it's actually going to come out like the stump is actually going to fall, like fly out of the ground at a larger force than either of the forces that were actually pulling it. So it comes out some roughly in the middle and it's a bit bigger of a force. All right, so let's go ahead and find theta now. Now you're welcome to use law of sines to find this because we do have a fully developed ratio. So you can use law of sines if you would like, or you can stick with law of cosines. It's completely up to you. I always think it's good to exercise caution when switching to law of sines, just because sometimes you end up with the wrong thing. But mostly that happens when you're solving an entire triangle. It doesn't happen as much with like these word problems and stuff. But if you want to just still be careful, you can go ahead and just still use law of cosines. I'm going to do that because that's what I like to do. So I'm still using this formula, but I'm going to solve it for the angle instead. So let's see if I solve this for like C or something. It would look like this. Nope. There we go. And if you want some practice on like actually solving that for the angle, I would go ahead and take a look back at 5.2. So here I'm going to get theta is equal to cosine inverse. And my like C in this case is my R, so 425.10 squared minus 300 squared minus 200 squared divided by -2 times 300 times 200. Also, be careful when you type this in. I usually like to put an extra parentheses for just the numerator and an extra one for just the denominator. You should get that theta is roughly, in my notes it says 25.2, but I'm going to still plug it in just to be sure. Oh no, I did this completely backwards. I am so sorry. When I typed this in just now, oh my gosh, I got 115 and I was like, what? That's not the angle I was looking for. I'm looking for theta. It's because when I plugged it in, I used this as my C. So I was finding the one across from that side. So let me erase this. Let me fix what I've got going on in here. Okay, if I'm looking for theta, the C that I put in should be the side across from theta. So it should be 200, should be that like C value. My other two sides should be the ones that are surrounding the angle theta. I'm glad I still typed it in instead of like just going with it and being like, yeah, that's right. And y'all would be like, no. What might have been helpful, and truthfully, what I should have done, and what you should probably do as well, is maybe like writing it out with the actual um, like angles and stuff like that before you put it in. So, for instance, I probably should have done this first and said, okay, it's 200 squared would be equal to 425.10 squared plus 300 squared minus 2 times 425.10 times 300 times cosine of theta. I probably should have written it out like that first and then moved it into the solving for theta form. That's just my bad. Hopefully it didn't mess you up too bad. Okay, let me retype this in to make sure that it's good. I try not to freak out or anything if I do make mistakes. I want to point that out to you, you know. Sometimes I like when they happen, truthfully. That way I can be like, oh, don't do this. So yeah, I got 25.2 as my answer. Now you want to be a little careful here with some of these because it's very possible that my math lab could get picky on the rounding and stuff like that. This one I just did one decimal place. That 425.10, since that's technically a rounded value, we may have wanted to use if you look at your calculator, you have like you have like an answer button. It says A and S. It's probably near your equal to sign. And so if you press second, you'll get to that A and S button and you can put in like a previous answer. So if you don't want to round or something, you might want to utilize that button. So just be careful. You'll notice like as you're doing the homework, sometimes the rounding kind of mess you up. Again, sorry about my mistake there. Hope it didn't mess you up too bad, but I hope you learned something and don't make that mistake for yourself. All right, let's go ahead to our next problem. This one's going to be example 2. The next type of equations that we're going to be looking at are force and weight problems. So before we start this one, I'm just going to say that up here. So these are force and weight problems. And I'm just going to make a few of them. So for the first one, it says the workers at Audubon Zoo must move a giant tortoise to his new home. Find the amount of force required to pull a 250-pound tortoise up a ramp the angle of elevation of the ramp is 30 degrees. And of course I'll make more, but I don't want to run out of space or anything. So, okay, I could show you how to draw this with like triangles, and it involves like making a parallelogram and stuff like that. Or I could just give you the formula. I think I'm just leaning towards giving you the formula. and I hope that that is okay with you. So the formula that we are going to use here is force is equal to weight times sine of your angle theta. Now, if you would like to see a video or something like that of how to actually get that formula, there are already some that exist and they're pretty good. Um, it's a little, I mean, it might feel a little physicsy, honestly, but I'm just gonna kind of give you the formula and go from there. Usually when I have shown the way to get the formula, it can be a little confusing. So I think that's just something that if you're interested in it, I would love to show you, or you can go kind of out of your way and um, you can look up a video or something like that on it. But I won't show it right this moment. Also, for the sake of time on this video, because I took way too long on that last problem, truthfully. All right. So if we're looking for force, so right, we want the amount of force. So we're looking for force. I have the weight, it's 250 pounds. And I need the angle of elevation. So my angle there is my theta. So my theta is 30 degrees. So I'm just going to go ahead and plug all this in. So I get force is equal to 250 times sine 30 degrees. Sine of 30 degrees is 1/2. So half of 250 is 125. And that would still be in pounds. So it's pounds of force. So hopefully not too bad, because you've got the formula there. Now this is not going to be a given formula. So be aware of that. I won't give that formula on the test. Let's do another one. This one says if a force of 86 pounds is required to push a safe up a ramp that is inclined 10 degrees, what is the weight of the safe? And now this one, I'm just going to tell you to round to the nearest. We'll do 10th for this one. And so usually like on the test and stuff, you'll notice that if your angle is like 30, 45, 60, or a reference of one of those, that's usually when I'm asking you to give your answer exact and not use a calculator. But for other ones where you have like weird angles and stuff, like this one, 10 degrees, I'm going to tell you to round because I would want you to use the calculator. So this one is going to be, again, we're using the force equals weight times sine of my angle. I have my force this time, so my force is 86. My theta is 10. And then I'm looking for the weight. So I'm looking for W. So I have, let's plug it in, I have 86 equals W times sine 10 degrees. I need to solve this for W, so I'll go ahead and divide by sine 10 degrees. And then from there, I'm just going to plug in the calculator. So I get W is equal to 86 over sine of 10 degrees. So I got 495.3. And this is still in pounds, just like the force was. So this was one where we had to find the weight instead. And we'll do one more. It says a motorist exerts 150 pounds of force to keep his 3,000-pound car from rolling down a hill. Find the angle of inclination of the hill. And I'll just say round to the nearest tenth. Again, if you see that you're looking at a problem that involves force and it involves the weight of something, and then it's talking about some kind of angle, you're definitely dealing with this formula. So you have force equals weight times sine of theta. He's exerting 150 pounds of force, so that's my F. 3,000-pound car, so that's my weight. And I'm looking for theta. So this one I'm going to have to solve for theta. So let's see, I get 150 equals 3,000 times sine of theta. Divide by 3,000. So now I have 150 over 3,000 is equal to sine theta. And always remember, if you're looking for your angle and it's not like a regularly known fraction on the other side, if it's a regularly known fraction, I usually recommend like using the table and using reference angles and stuff like that. But this is not one that we can do that. We were also hinted towards it because it told us to round. So we're going to have to use sine inverse for this one. So theta is going to be sine inverse of the other side. So I'll plug that all in and it gives me, let's see, let me plug it into my calculator. I get 2.9. So that's it for our force weight problems. Hope they were all right. Now I'm going to go over to our next type of like application problems, and these are airplane problems. So that's our next like type of problems that we're going to see. First, I want to go over a few things with you while we deal with airplane problems. The first thing is our coordinate plane is going to be a little different to look at. So when we're dealing with airplane problems, we're going to be talking about directions, so north, east, south, and west. So that's also going to change where like our degrees and stuff fall. So usually we would start over here and we would say that this is 0 degrees. Now our 0 degrees is at the top. Also, usually we would go counterclockwise. Now we're going to go clockwise. So this is 0 degrees. This is 90 degrees. This is 180 degrees. This is 270 degrees. And this loops back around to 360. So our coordinate plane looks a little different than what we usually use. Now the rest of it, I really think it's just going to be easier if I like start on an example and just kind of talk you through it. So I'm going to go ahead and do that. But we're going to be dealing with triangles in this section. So usually I'll give you kind of a rundown of what we're going to see. It would be like we're going to have a plane trying to go a certain way, and then the wind is going to be pushing on the plane. And so we're going to have to figure out where the plane actually goes because of the push from the wind. That's the gist of these problems. So let me go ahead and write one out for us. So this is example 3. So it says an airplane is headed due west, which means it's bearing 270 degrees. They often won't tell you both of those pieces of information, but this is our first one, so we're kind of giving you a lot of information. With an airspeed of 250 miles per hour. The wind is from the north, bearing 180 degrees at 30 miles per hour. We want to find the ground speed the drift angle, and the course, or sometimes they'll call this bearing, of the plane. So of course pause and go ahead and write all that out. First thing we should always do with these is draw. So let me go ahead and draw our new coordinate plane. So I have north up here, that's 0. I have east over here, that's 90. South is 180, and west is 270. So we'll always say that the plane is going to start from the origin. So we're saying this plane heads due west, which means it's bearing 270 degrees with an airspeed of 250. So that means that the plane is going this way, and it's 250 is like the size of that vector. So remember that vectors will always have a magnitude and a direction. So the direction is that we're going towards 270 degrees. The size is 250. So that's also making it like kind of long. Then we want to look at the wind. So the wind is from the north and it's bearing 180 degrees. So the wind, technically, you can draw it wherever you want. So you can draw it all the way starting up here if you want and draw it down. Usually with vectors, we would start at the tail of our last vector and we would say it's only 30 miles per hour, so it's not very long. So I'm just going to draw it not very long. And so just a reminder, so that's happening from, it's coming from the north, so that's why I'm drawing it like downwards like this, bearing 180 degrees. Now, sometimes what I'll see people do is they'll draw it right here. But let me be clear to you, the plane is not in the middle anymore, right? So the plane is like flying. So the reason we want to draw it from the tip of our last vector is because that's where we're saying the plane is at this instant. If you draw it from the other way, you end up making, I mean, in this case, it would be a rectangle, but we will do something like that later and we'll have to make a parallelogram. I'm not going to get all into that yet. We're not there yet. Okay, so far we have our plane and we have the wind. Now I want us to think about where our plane is actually going to go. So like the plane is trying to go straight 270 degrees. The problem is as it's flying, the wind is like pushing it down. So the plane is actually going to go this way. So this blue line that I just drew, that's where the plane is actually going because the wind is pushing it down. And so there's a few things that we'll find here. I want to know how fast does the plane actually go? Because like it's trying to go 250 miles per hour, but it's being pushed by the wind. So it's actually going to either go slower or faster than that. We'll see. So that's the ground speed. Really what it is um, it's the other side of our triangle. It's the missing side of our triangle. The drift angle is how far between where the plane was trying to go and where the plane actually went. So drift angle is always going to be the inside angle between where your plane was trying to go and where the plane actually went. So it never touches the wind. It's always going to be across from the wind. And then lastly, we'll have the course or the bearing of the plane, and that'll be like the degrees of this blue line. Like where is this blue line actually going? So first, let's go ahead and find our g. So we're finding our ground speed. Now here's the problem. I always need like 3 pieces of information to find out other stuff about a triangle. Right now, it looks like we only have 2 pieces of information, but we can always find what the angle between where the plane was trying to go and the wind, we'll always be able to find that angle inside of there. So in this case, if you have a straight horizontal line and then a straight vertical line, that's going to make a 90-degree angle inside of there. So our angle inside there is 90 degrees. That actually makes this a pretty simple problem because if it's 90 degrees, means we have a right triangle. So we can use like Pythagorean theorem and like sine, cosine, tangent, and all that kind of stuff. So when I find my g here, I can use Pythagorean theorem. So g squared is equal to 30 squared plus 250 squared. And I can take the square root. And let's see what I get. I get 251.8. So this is my ground speed. This is how fast the plane actually goes. It would be in miles per hour as well, just like the other sides of the triangle were. So it's getting pushed a little bit faster, just a little bit. Usually like where your plane was, like how fast it was trying to go, and your ground speed are not going to be super far from each other because the wind usually, unless we're like flying in a hurricane or something, is not like that strong. Next, let's go ahead and get our drift angle. So my drift angle, there's a few different ways you can get it. You can use sine, cosine, or tangent. The reason I would recommend tangent for this one, so tangent of theta would be equal to the opposite side over the adjacent. So in this case, that would be 30 over 250. The reason I would use tangent for this is because then you don't have to use the hypotenuse. You don't have to use a rounded value. It won't be really a problem if you do that on the test, like, because if on the test you're a little bit off by a few decimal points, it's really not a big deal. But for the homework, it might frustrate you. So this would be tangent inverse 30 over 250, and I'm going to plug that in and see what I get. I get 6.8 degrees. So this is my drift angle. This is how far the plane got pushed off of its original like heading because of the wind. And usually your drift angles are pretty small. Now the last thing I need to go get, let's see if I have another color I can use. I don't have like an orange on here. Let's go get an orange. That's like an ugly orange. I want like a cute orange. No, that's an ugly orange. Maybe if I go like higher up. I want like pumpkin orange, you know? Okay, that's good. That's good. It really doesn't matter, but I wanted the color to be like to stand out is all. All right, so now let's find the course or the bearing of our plane. So that's telling us like how, like where the plane actually goes. How far off of its track did it go? Because it was supposed to be going 270 degrees, but it got pushed this way by 6.8 degrees. So now I want you to think. Do you think we should add 6.8 to 270 or should we subtract it? Should we add it or should we subtract it? So what I want you to notice is we're trying to get closer to the bottom, which is 180. So we're going from 270 closer to 180. So since we're getting smaller, we want to subtract. So our course or the bearing is 270 minus 6.8 degrees. So that's going to be 263.2. So that's where the plane actually went. When it comes to finding the course, um, you don't want to look too much on going like up or down, because what you'll notice over here is if we had gone, like, let's say the plane had been going 90 degrees and we'd gone down like this, we would have actually added our drift angle. It's really more about the direction in which you go, like around the coordinate plane or the compass or whatever. So in this case, we ended up subtracting, and if you notice, we went counterclockwise. So I'm going to write that for us. So counterclockwise, you're going to subtract your drift angle. If you go clockwise, so if you go like with you go this way or this way or wherever you're at, then you're going to add your drift angle. And so it's better to just kind of make sense of it, of course, but that is going to be kind of the rule that we'll see happen. All right, let's go ahead and do another one of these. So this one is example 4. This one says an airplane is headed due east with an airspeed of 300 miles per hour. The wind is out of the northeast bearing 225 degrees at 50 miles per hour. And we're going to find the ground speed, the drift angle, and the course of the plane. So finding all the same stuff, given all the same information. So I've got north, which is 0, east, which is 90, south, which is 180, and west, which is 270. So I always like to draw it out first. The plane is headed due east with an airspeed of 300. So always draw it from the middle at first. And so it's going to the east with a speed of 300. the wind is out of the northeast. So we want to think, where is the northeast? So northeast is coming out this way. So basically the wind is hitting like this, like in that shape. You got to remember, wind, it's not like it just hits in one spot. Like wind is just blowing down. So, but we got to figure out how to actually draw it like on our picture. It also says that it's bearing 225 degrees. So if we look at like what 225 degrees would look like just on our graph, like right now. So 225 would be right between 180 and 270. So it'd be like right down the middle here. So what we're going to do, I'm going to draw it a little shorter. So what we're going to do is we're going to draw it off of the edge of our last vector, but in the same like angle. And let's think of something else. We're going to need to know that angle inside of there. So I'm not going to tackle it right this second, but we will. And then we're trying to figure out stuff about where the plane actually went. So the plane is getting pushed downwards, so it's actually going to go like here. Try to make it a little darker. There we go. And so we're going to have to find the size of this, so that's going to be G. Our drift angle is always between where the plane was trying to go and where it actually went, always across from the wind. So I'm going to put that here, which is theta. And so we have a triangle, but we only have two pieces of information right now. We have to go find out the angle between where the plane was trying to go and the wind. To get that angle in this case, we're almost going to kind of use like a reference angle. So if you look here, this is straight horizontal. This is 225 degrees. So my question to you, how far away is 225 from 270? It would be 45 degrees. That means that over here, this is also 45 degrees. And so what's really happening here, I know it's kind of crazy to think about, but these are parallel lines and they're being cut by a transversal. And so we're actually seeing corresponding angles happen. So we take that in for a second. The way I got that it's 45 degrees inside of there is because I knew that this line over here, this one, was 225 degrees, and that was my wind, was coming at 225. If I look at how far that is from the horizontal, I'm getting 45 degrees right there. I'm doing 270 minus 225. So then I draw that in my actual triangle. And we can do another one like this as well. I would like to make another one. So now that we have a triangle with three pieces of information, we can go find everything else. But it's not as easy as example 3. Example 3, we had a 90-degree angle in there, which was so great. Makes it so much easier. This one, we don't. So this one is not a right triangle. So with that being said, you can either use law of sines or law of cosines? Now, because it's a side angle side, so we're going to pick law of cosines. We can't use law of sines for this one. So law of cosines, I'm going to go ahead and write out the formula for us. Hopefully I don't mess it up like earlier. So a squared plus b squared minus 2ab times cosine of c. I'll try to label a little bit better for this one. So this one will be my a and this one will be like my b. So I'm going to plug it in to go and find g. So g squared is equal to 50 squared plus 300 squared minus 2 times 50 times 300 times cosine of the angle across from G, which is 45 degrees. Remember to take the square root, and we should get that G is approximately, and I'm going to go plug it in. So give me just a second. You can try to plug it in as well. I get 266.99587. So I'm just going to say 267.0 is my ground speed. Next, let's go get my theta. So again, I like to use law of cosines again. You are welcome to switch to law of sines if you want. I've just always liked to stick with one if I start with it. I don't really like to switch. So I'm going to go find my theta. Now, what I messed up on earlier is I put in the wrong one like across from it. So let's not do that this time. So for this one, if I'm trying to find theta, if I put it into the original equation, it would be 50 squared is equal to 300 squared plus g squared minus 2 times 300 times g times cosine of my theta. Now I have g, so I'm going to go ahead and plug that in. Be careful when you do it through my math lab though. You may not want to actually round, like use your rounded value, unless it tells you that you can. So if I write all this out, it would be 50 squared minus 300 squared minus 267 squared divided by negative 2 times 300 times 267. And I always put an extra parentheses around the numerator and denominator. I got 7.61 degrees as my drift angle. Now, if yours is a little bit off from me, it may be a rounding thing because I didn't actually use 267. I used like this answer button, like the last answer, and used my actual G that was already in the calculator. So I didn't round at all to get that value. And we should always expect it to be pretty small. Lastly, for my course or the bearing of the plane, I got to decide where the plane was trying to go. So it was trying to go 90 degrees. And then it's getting pushed downwards by 7.61 degrees. So are we going clockwise or counterclockwise? We're going clockwise, so we're going to add our drift angle. Or you can think of it, we're getting closer to 180, so we want to get bigger. So this would be 97.61 degrees is the course or the bearing of the plane. So this one was a little bit more complicated because we had to use law of cosines on it. I'm just kind of sitting on it for a second before I move on, but you're welcome to, just kind of pause and take it all in and stuff. I'm going to go ahead and move on though. I think I want to do one more like this. So if you felt good about that one and you feel like you don't really need to see the next one, I mean, that's fine. I'm at least just going to like set it up. So let's see. An airplane is headed due west with an airspeed of 425 miles per hour. The wind is out of the dun dun dun. What do I want to pick? Let's do northeast. But it's bearing 210 degrees. And find ground speed. Oh, I didn't say how fast it was going. My bad. Hold on. Erase, erase. There we go. 210. Let's just say at, sorry, this is what happens when I make them up, but it's good for me too. At, we'll just say it's like 40 miles per hour. And then we'll find ground speed, the drift angle, and the course or the bearing, whatever you want to call it. All right. I at least just want to set this one up. So I've got north 0 degrees, east 90, south is 180, and then west is 270. So our plane is heading west. So I'm starting from the middle and it's going to the west, 425. Now the wind is out of the northeast bearing 210. If we actually just draw where 210 would be like right here. So this one is actually pretty easy to find. I kind of messed up making it, but that's okay. It's still good for us to look at it just to get some more experience. So this one is interesting because if you just draw the wind from the middle, you get that this angle inside of here from the wind to the 270 is 60 degrees. However, this one's a little tricky. That's not your drift angle. It might seem like that's your drift angle, but it's not. The point is that the plane is going to cut through this, right? So 60 degrees is not our actual drift angle, even though it may have seemed like it for a second. No, we would have to do to find the other angle across from that. So this one actually introduces us to almost the parallelogram idea, where if I'm looking for this angle over here, so this one was a little harder than what I was expecting. If I'm looking for that angle over there, I would do 180 minus 60. Which is going to give me 120. So this angle over here is 120 degrees. And so now I'll have all my information. This is still 40, but it was a little bit weird how we had to get that extra angle. So just depending on your problem, you may have different things to do. This one introduces us to the next type of problem we're going to do actually pretty well. So I'm glad I did it, but it was harder than I expected to make it. And it could change. Like, what if I had changed it to, like, what if I had made a new one and I had said all the same information, but I said wind is out of the northwest bearing, let's say it's bearing, let's say 145 degrees. It doesn't have to be one of the known angles that you know about. So 145 for this situation. I'll draw again like what we're seeing happen. So we got north 0. Plane still going this way. But now it's coming out of the northwest. So it's coming out like this way. So my angle here is 145. And so you see how I'm drawing it the same, like from the middle to kind of get the shape of it, but then I'm drawing it on the actual like tip of the plane or the plane like vector. And so for this one, I would say, okay, 90 to 145, how much is that? 55 degrees. So that means that this inside angle here is 55 degrees. So I'll let you kind of do those maybe if you would like to, just practicing using law of cosines with them. But those are just two other like cases, to show you how to find that missing angle inside of there. All right. Now, this last example is a little hard. The reason is because on the first example, both our plane and our wind were at like horizontal and vertical um, positions, I guess I could say. So we made like a right angle inside of there. Then in our next examples, we saw the plane was always at a horizontal and then the wind was just at a weird angle. On the homework, there's an example that you'll do that it has like the wind coming in at a straight angle, but it has the plane coming in at like a weird angle. So I'll show you what I mean by that. The one on the homework, I don't want to completely set it up for you, and I won't tell you which one it is, but it's something like this. The plane is like at like a weird-ish angle, and then the wind is cutting it like this. And so it's something like that. And what's happening though is as long as either the plane or the wind is coming at like a horizontal slash vertical respectively, the problem is a little bit easier. If both the plane and the wind are at weird angles, the question can get a little harder. And so that's what we're going to do right now. We're going to do one like that. So let me write it out for you. It says the heading of a Learjet, I don't know what that is, has a bearing, a plane. That's what it is. Has a bearing of 320 degrees. The wind is 70 miles per hour with a bearing of 190. If the airspeed of the plane, or the jet, whatever, is 400 miles per hour, find, and we're going to find all the regular stuff, ground speed, drift angle, all that. So of course, always want to draw it out first. So I'm going to try to draw this one fairly big actually because there's going to be kind of a lot of different parts to this one. Okay, that looks terrible. I can't leave it, sorry. Okay, that's maybe a little better, not really. So then top is north 0, east is 90, south is 180, and west is 270. All right, so the plane coming in with a bearing of 320. So 320 is going to be between 270 and the 0, which wraps around to 360. So I'm going to draw it, I don't know, like probably like here. I mean, it doesn't really need to be perfect. And so that has a airspeed of 400 miles per hour. So I'm just going to draw that on there as well. Now the wind is 70 miles per hour with a bearing of 190. So 190, if I drew it from the middle, is something like this. So I'm going to go draw that on the other side of my vector. I don't want it too long because it's just the wind. So I'm just going to shorten it a little bit. Okay. I'm going to label some other stuff for this one. So my pink line, where the plane was trying to go, that was 320. My green line down here, this is 190 degrees. That's going to be important, so I want us to see like where it went. And then the plane is actually going to go through here. Well, yeah, there we go. So it starts here, and it's just getting pushed like downwards a little bit. Also, sometimes you can kind of tell by the picture, like whether or not it should be like slower or faster or whatever. For this one, it looks like the blue is ending up a little bit shorter, so I probably should expect the plane to end up a little slower. And some of the ones from earlier, this one on the left that I drew, it looks like the plane should go faster. So my ground speed should go faster. The one on the right that I drew, it looks like it should go slower because the wind is like pushing it backwards. So you can kind of think of that as well as you do these. Like what should you expect your G to be? Should it be bigger or smaller than where the plane, how fast the plane was trying to go? All right, my drift angle is still in the middle right here, always across from the wind. And I didn't put the wind speed. Let me put that on there, 70. And so this is G. All right, so pretty much what happens here is that we've got a parallelogram. Very similar actually to what I showed you on the left up there. It's going to be like a similar process. So remember that with parallelograms, this angle and this angle are supplementary. So what's going to happen there is we can find the angle on the right, and we're going to use that to find the angle on the left. So the angle on the right, I see that the pink line here, where the plane was trying to go, is 320 degrees. This green line down here with the wind is 190. So my question to you is, how big is this spot right here? How much is it from 190 to 320? So you should get 130 degrees there. So then over here, because we always want the angle across from the G, across from the ground speed, that way we can have like at least a side angle side relationship. It's because we need 3 pieces of information about the triangle. So if this over here on the right is 130, and 2 adjacent angles are supposed to add to 180, this angle here must be 50. And so let me show you again how I got that. So I did 320 minus 190, and that's how I got 130. Then I did 180 minus 130 because those are supplementary angles, and that's how I got 50. So now I have my triangle and I have 3 pieces of information, so I can move to using law of cosines. So to find G, I'll have 70 squared plus 400 squared minus 2 times 70 times 400 times cosine, and the angle across from G is 50 degrees. And don't forget to take the square root. I'm going to plug this in and tell you what I get. I get 359.0 as my ground speed. Next, I can go get theta, so my drift angle. So my side across from it is 70. My two sides surrounding it are the G that I just found and 400. So it'll be 400 squared plus G squared minus 2 times 400 times G times cosine of theta. Just want to make sure that this one and this are across from each other. I'm going to go ahead and solve this for theta. So cosine inverse, it'll be 70 squared minus 400 squared minus my G, which is 359. Be careful, I'm not actually going to plug in 359. I'm going to use the unrounded value. Just make sure you have parentheses around the whole denominator and whole numerator. For my theta, let me go ahead and plug it in and I'll tell you what I get. So again, I did not round at all and I got 8.6. So that's my drift angle. And then lastly, my course or my bearing. I'm going a little faster here because it's just not, it's kind of repetitive, like this part of it, you know, like using the law of cosines and stuff. The hard part is really the setup and getting that inside angle. So then the course or bearing, so I originally went 320 degrees. So that's where the plane was trying to go. And then it got pushed this way. So it got pushed downwards, right? So that's where the wind was going. So should I subtract or should I add my drift angle? We're going counterclockwise, so we're going to subtract. So this one we're going to do for my course, I'll do 320 minus 8.6, and I get 311.4. So that's where the plane actually went. So it was trying to go 320 degrees, but it actually went a little bit lower than that. I want to tell you something kind of cool, I guess. I knew someone who was like in a pilot and stuff, and she told me that I was curious, you know, so I asked her like, "Hey, do y'all do any of this at all? Like, is this actually important to your job?" And she was like, "Well, I'll be honest, the computer does it for us, you know, like it calculates, you know, how fast the wind is going and how far off track like we're actually being pushed. So the computer does it for us." However, she said that one time when she was flying, the computer went out and she was like, maybe it could have been helpful for me to know how to do it because I did almost get lost. Um, However, I'm not sure if I was flying a plane, like I'm saying this, I don't know that if I was flying a plane, I would stop real quick and like do a math problem. You know what I mean? However, I do think it's cool that she did say that she had to learn it just because you know, but the computer does do it for her. So there you go. It's kind of useful. That's what I got from that. But that's it for us for this section. The airplane problems, you know, there's different types and stuff, so you have to be prepared to see any of them on the test. Definitely seeing a force and weight problem. Um, this problem, I mean, you definitely could see it, the horses one, but it was mostly just to introduce us to like using a parallelogram. But you could see it on the test. So if you have any questions, please remember to reach out to me. I would love to meet with you and help you out with anything that you're needing. Hope you'll have a good day and a good week. Bye bye.